Welcome to the Deep Sleep Science Channel. Tonight, we're drifting into the quiet, glowing clouds of the universe, places where stars are born, where stars come to an end, and where the matter that once formed distant suns slowly gathers again to begin something new. Some of these nebulae are so vast they stretch across dozens of light years, yet they are so delicate that, if you could pass through them, you might barely notice the particles around you. Others were created by explosions so powerful they briefly outshone entire galaxies, leaving behind soft, glowing remnants that still move and change even now. As we move through these cosmic clouds, you'll discover how light can sculpt gas into towering pillars, how hidden stars glow behind curtains of dust, and how the universe quietly recycles itself over and over again. And before you begin to fully relax, you can gently like, subscribe, or leave a comment. It helps the channel grow, and you can do it now, before sleep slowly takes over. At the center of the Crab Nebula is a neutron star, the collapsed core left behind after that supernova. It is an object of incredible density, made when a massive star's core was crushed down after the explosion. What remains is not a normal star anymore, but a tiny, extreme remnant that still powers the nebula around it. That central remnant in the Crab is also a pulsar, and it spins about 30 times every second. As it turns, beams of radiation sweep through space, so from Earth it can seem to flash on and off like a lighthouse. It is one of those cosmic objects that feels almost mechanical in its regularity, even though it was created by one of the most violent events in nature. Even more astonishing, the Crab pulsar is only about 6 miles across, yet it contains more mass than the Sun. That means an object smaller than many cities holds more matter than the star that lights our whole solar system. It is a reminder that in astronomy, size and power do not always go together in the way they do in daily life. The eerie blue glow inside the Crab Nebula comes from electrons moving near the speed of light around magnetic field lines. This process creates a kind of radiation that lets astronomers trace the motion of extremely energetic particles. So when people admire the color of the Crab, they are also looking at physics in action on a truly extraordinary scale. The Crab Nebula is not simply leftover debris fading away in silence. It is a pulsar wind nebula, which means the spinning pulsar at its center is still injecting energy into the surrounding material. That is why the nebula remains active and structured, with motion and light still being driven from within. Over many years of observation, astronomers have seen that filaments near the Crab's outer edges have moved outward more noticeably than material closer to the middle. This lets scientists track expansion over time instead of only imagining it. In other words, this nebula is not just beautiful in pictures. It is visibly changing. The Crab also shows rings, wisps, and jets around its pulsar, revealing that a nebula can have fine structure as well as broad shape. These features help researchers understand how energy flows outward from the central remnant. Even centuries after the supernova, the Crab is still a dynamic and restless place. The Tarantula Nebula, also called 30 Doradus, is the largest known star-forming region in the local group of galaxies. It is not in the main disk of the Milky Way, but in the large Magellanic Cloud. Even at a distance of roughly 170,000 light-years, it stands out as one of the most spectacular stellar nurseries known. At the heart of the Tarantula lies the giant young cluster R136, which contains some of the most massive stars astronomers have ever found. Several of those stars exceed 100 times the mass of the Sun, and some have been described as around 200 solar masses. These are stars so extreme that they help define the upper limits of normal stellar life. R136 is also remarkably young. with its oldest stars only about 5 million years old. In human terms, that sounds ancient, but for stars, especially massive ones, it is very young indeed. And even while that cluster already blazes with energy, smaller stars are still forming in and around it. The tarantula is so useful to astronomy because it is close enough to study carefully, yet powerful enough to resemble giant starburst regions seen in more distant galaxies. It acts almost like a nearby model of much more extreme cosmic environments. That makes it both beautiful and scientifically precious. In the Carina Nebula, one of Webb's most famous views shows the so-called cosmic cliffs. These are not mountains at all, but the illuminated wall of a cavity inside a nebula. The scene looks like a landscape only because light, dust, and distance arrange themselves into something our eyes interpret as terrain. That cavity in the cosmic cliffs lies about 600 light-years away, and it was carved by ultraviolet radiation and stellar winds from hot, massive stars above the scene. So what looks still and peaceful in an image is actually the result of ongoing pressure, heating, and erosion. The cliffs are a record of starlight physically reshaping matter. Within the cosmic cliffs, astronomers see dust pillars, stellar jets, and misty streams of ionized gas. These are signs that the region is not only being carved apart, but is also involved in fresh star formation. It is a place where destruction and creation are happening side by side. The famous pillars of creation in the Eagle Nebula stretch roughly 4 to 5 light-years. They are columns of cool hydrogen gas and dust, and they function as incubators for new stars. Their dramatic shape comes from the fact that denser material resists erosion longer than the surrounding cloud, leaving behind towering structures. Those pillars are being sculpted by radiation and strong winds from hot young stars in the nearby cluster NGC 6611. Their glowing edges are created where dust and gas are heated and ionized on the surface. So the bright rims and dark interiors together tell the story of a cloud being slowly worn away by nearby stars. The Horsehead Nebula, also known as Barnard 33, is one of the most recognizable dark nebulae in the sky. In visible light, it appears as a dark silhouette against the brighter emission nebula, IC 434. Its shape resembles the head of a horse or even a chestnut, which is one reason it has become so famous. Astronomers think the Horsehead may disintegrate in about 5 million years. That sounds like an impossibly long time to us, but in cosmic terms it is relatively brief. It survives now because its clumpy, dense material resists erosion better than the gas around it, but even this striking shape is temporary. The homunculus nebula was created by Eta Carinae during a great outburst in the 1840, making it exceptionally young by nebula standards. It is about a light-year long, and the eruption threw at least 10 times the Sun's mass out into space, perhaps more. Few nebulae allow us to study such a dramatic stellar event that happened so recently in historical time. Eta Carinae itself is one of the most massive binary systems that astronomers can study in detail, and modern modeling suggests that its binary nature helped shape the homunculus. The system is expected to end its life in collapse, probably as a supernova. So the nebula around it may be only one chapter in a still unfinished story. The Orion Nebula is the closest large star-forming region to Earth, lying about 1/500 light-years away. Because it is both nearby and bright, it can be seen without optical aid under decent skies. That makes it one of the few places where people can look up and directly glimpse an active stellar nursery. Orion spans roughly 24 light-years and contains hundreds of newborn stars. In detailed Hubble views, more than 3 000 stars can be seen in a single image. It is often called a picture book of star formation because it shows many stages of stellar youth in one region. Inside Orion are protoplanetary disks, often called proplyds, surrounding very young stars. These disks are thought to be about 99% gas and 1% dust, and some of them are being stripped by intense ultraviolet radiation from nearby hot stars. Orion therefore shows not only how stars form, but how fragile young planetary systems can be in crowded environments. A nebula is a cloud of gas and dust in space, and it can appear bright or dark depending on how it interacts with light. That simple definition covers a huge variety of objects, from star nurseries to the remains of exploded stars. So the word sounds gentle, but it includes some of the most active places in the universe. The word nebula itself was once used much more broadly for many fuzzy-looking objects in the sky seen through early telescopes. Before astronomers understood the true nature of galaxies, star clusters, and gas clouds, many of them were grouped together under that one loose label. The history of the word reflects how human understanding slowly became more precise. Today, astronomy separates nebulae into several main categories, including emission nebulae, reflection nebulae, dark nebulae, planetary nebulae, and supernova remnants. These groups are based on what the nebula is made of, how it shines, and what event or process created it. So classification helps turn a beautiful blur into a physical explanation. Emission nebulae glow because energetic stars ionize nearby gas. In simple terms, strong ultraviolet light from hot stars strips electrons from atoms, and when those electrons later recombine or shift energy states, the gas emits light. What we see as a glowing cloud is therefore matter being energized by nearby starlight. Reflection nebulae shine in a different way. Instead of producing much of their own visible light, they scatter the light of nearby stars. They often look blue because shorter wavelengths scatter more efficiently off fine dust, much the way Earth's sky looks blue because of the way light is scattered in our atmosphere. Dark nebulae are seen mainly in silhouette because dense dust blocks the light of brighter material behind them. They are not empty holes in space, but thick clouds that hide what lies beyond. In many cases, these dark regions are also cold and dense enough to become places where new stars can begin forming. Planetary nebulae are not related to planets at all. The name remained from early observers who thought their small, round disks looked somewhat planet-like through older telescopes. In reality, a planetary nebula forms when an aging star sheds its outer layers and leaves behind a hot white dwarf at the center. Supernova remnant nebulae come from a completely different kind of ending. Instead of a gentle shedding of outer layers, they are made from the debris of exploded stars. That means nebulae can represent both slow stellar aging and catastrophic stellar death, depending on which kind you are looking at. Nebulae are not just visual decorations spread across the galaxy. They are major parts of the cycle by which stars are born, evolve, and die. In that sense, they are part of the universe's recycling system, holding raw material, processed material, and the traces of stellar change. Dust inside nebulae can hide stars in visible light, while allowing infrared telescopes to reveal them. This is why the same region can look almost empty in one kind of image and crowded in another. Dust blocks shorter wavelengths well, but infrared light can pass through more easily. Because of that, infrared observations often show that a place looking dark in visible light actually contains warm dust and embedded stars. A cloud that seems like an absence can turn out to be full of hidden structure. Nebulae teach astronomers not to trust a single wavelength too quickly. Ultraviolet radiation from hot young stars can sculpt nebular clouds by heating, ionizing, and eroding their surfaces. Over time, that radiation can carve ridges, bright rims and cavities into the cloud. So, starlight is not only something that reveals a nebula, it can physically reshape it. Stellar winds from massive stars can excavate large cavities inside nebulae. These winds are streams of charged particles flowing outward from stars at high speed. When many powerful stars act together, they can blow out enormous hollowed regions in the surrounding gas. Some nebula pillars exist because denser clumps resist erosion longer than the material around them. As radiation and winds strip away softer regions, the tougher pockets remain standing. That is why some clouds end up looking like towers, columns, or fingers pointing through space. Nebulae often look richly colored in telescope images because different filters isolate light from different chemical elements. A telescope may record separate emissions from hydrogen, oxygen, or sulfur, and then combine them into a final image. The result is not random color, but a map of physical differences in the cloud. In many published nebula images, hydrogen and sulfur are mapped to red tones, while oxygen is often shown in green or blue. These choices help astronomers and viewers distinguish one kind of glowing gas from another. So color in nebula imagery often carries scientific meaning as well as beauty. Dusty regions inside nebulae can act as natural incubators for stars and, later, for planet-forming disks. As gravity pulls material inward, dense cores can grow until new stars ignite. Around some of those newborn stars, disks of gas and dust may later give rise to planets. Many of the most famous star-forming nebulae are H2 regions, meaning regions of ionized hydrogen. The term sounds technical, but it simply refers to hydrogen atoms that have lost their electrons because of strong radiation from hot stars. These regions glow because the gas is energized and lit from within. The Orion, Lagoon, Rosette, and NGC 346 regions all show how H2 regions can range from nearby local examples to distant extragalactic laboratories. They belong to the same general family, yet each reveals a different environment and scale. Together, they show that the same physical principles can appear across very different corners of space. Nebula brightness is not always caused by the same process. Some nebulae glow through ionization, some by reflected starlight, and others mainly by heated dust, seen in infrared light. That means the glow of a nebula is not one single phenomenon, but a collection of different ways matter can interact with radiation. A nebula can even combine several of those processes at once. One region may contain glowing gas, dark dust layers, and reflected starlight altogether, creating a mixed appearance. That is one reason nebulae can be visually complex and scientifically rich at the same time. Nebulae can span an enormous range in scale, from small cometary knots in a planetary nebula to vast star-forming complexes like Carina and Tarantula. Some fit within a fraction of a light year, while others stretch across tens or even around 100 light years. The same word then covers structures of very different sizes. High-energy radiation can make nebula edges look bright where an ionization front is striking the gas. This creates glowing borders, rims, and outlines that can look almost sharp compared with the softer interior. What seems like a neat edge is often a boundary where physical conditions change quickly. Dense clumps inside nebulae often survive longer than the surrounding material, creating pillars, nops, and globules. These darker or denser pockets can cast shadows and reshape the flow of radiation around them. Much of a nebula's texture comes from this uneven resistance to erosion. In star-forming nebulae, erosion and compression can happen side by side in the same cloud. Radiation may tear material away from one region while helping squeeze another region into denser form. So the same force that destroys one structure can help set the stage for new stars elsewhere. Nebulae often reveal timescales that are enormous by human standards, but short by stellar standards. A shape may last millions of years and still be temporary in cosmic terms. Nebulae are a good reminder that the universe changes slowly to us, but not necessarily slowly to itself. Planetary nebulae are temporary structures and do not last for the whole lifetime of a star. One general estimate says such a nebula fades away after roughly 100,000 years. That means the glowing shell is only a brief final display in the much longer life story of the star that created it. A planetary nebula comes from a sun-like star shedding outer layers, while a remnant like the crab or veil comes from a stellar explosion. So even though both are end-of-life nebulae, they come from very different kinds of parent stars and very different endings. Their outward beauty can hide very different origins. The central stars of planetary nebulae are white dwarfs, hot compact leftovers from stars that have lost much of their mass. They are tiny compared with the broad shells surrounding them, and yet they provide the ultraviolet radiation that lights those shells. A small remnant can therefore dominate an enormous surrounding cloud. Nebulae are major recyclers of matter, returning processed gas and dust from old stars back into interstellar space. In star-forming regions, that recycled material can later become part of future stars and even future planets. The matter does not simply vanish. It changes role. Despite their dramatic appearance, nebulae are extremely tenuous compared with Earth's atmosphere. They look solid and thick in pictures, but the particles within them are usually spread very far apart. Their visibility comes not from density, but from great size, illumination, and the sensitivity of modern instruments. The most famous nebulae are usually not isolated objects floating alone, but parts of larger molecular clouds, shells, or stellar complexes. They belong to wider environments that connect individual stars to cluster life and galactic structure. So a nebula is often best understood as one scene inside a much larger story. Taken together, nebulae show that space is not empty background, but an active medium where matter is continually being illuminated, rearranged and reused. They connect stellar birth, stellar death, and the recycling of cosmic material into one ongoing process. When we look at nebulae, we are really looking at the universe in the middle of becoming something else. The Orion Nebula is bright enough that under reasonably dark and clear skies, people can see it without any optical aid at all. That is unusual for a nebula because many of them are too faint to stand out to the naked eye. Orion's apparent magnitude is around 4, which helps explain why it has been noticed for so long. Even before modern telescopes, it was already there as a visible soft patch in the night sky, inviting people to wonder what it was. In the sky, the Orion Nebula sits in the sword hanging below Orion's belt. This makes it easier for sky watchers to find because the constellation Orion is one of the most recognizable patterns in the heavens. Once you know where the sword is, the nebula becomes one of the most rewarding objects to look for. It is a reminder that some of the most important places in astronomy are also among the easiest to locate. Orion's famous trapezium can be resolved with binoculars or a telescope under suitable observing conditions. This little grouping of bright young stars sits inside the nebula and helps light the surrounding gas. For many observers, seeing the trapezium for the first time is a special moment because it reveals that the glowing cloud is not just empty mist. It is an active, stellar environment, with young stars shaping the entire region around them. The Orion Nebula has been recognized by different cultures for a very long time, not only by modern astronomers. Human beings noticed this glowing patch long before they understood star formation or spectroscopy. That means Orion is part of both scientific history and cultural history. It has belonged to the sky stories of humanity for far longer than it has belonged to astrophysics. In Mesoamerican tradition, the Maya associated the Orion Nebula with cosmic fire of creation. That is a striking idea, because modern astronomy also sees Orion as a place where new stars are being born. The old symbolic meaning and the modern scientific meaning are not the same, but they overlap in a beautiful way. Both see this region as connected to beginnings. When astronomers look at Orion in infrared light, it appears very different from how it looks in visible light. Warm gas and dust begin to stand out much more clearly, while the obscuring effect of dark clouds becomes less severe. This allows scientists to look deeper into the nebula's hidden interior. In simple terms, infrared light helps reveal what ordinary vision leaves concealed. In infrared views of Orion, hydrocarbon-rich dust can be separated from starlight and warm gas. This matters because it lets astronomers study different ingredients of the nebula one by one, instead of blending them all together. A visible light image can look like one glowing scene, but infrared observations break the picture into its separate physical components. That is one reason modern astronomy learns so much by observing the same place in multiple wavelengths. A separate infrared survey found a giant nebula around Lambda Orionis, making Orion's head appear much larger than it does in visible light. This is a good example of how the familiar shapes of constellations are only part of the real story. What the eye sees is often just the brightest and clearest layer. Infrared observations can reveal surrounding structures that are much broader and more complex than the traditional outline suggests. The Eagle Nebula is a vast star-forming region in the constellation Serpens. It is much larger than the famous structures most people recognize from photographs. When astronomers describe it as a star-forming region, they mean it is a place where clouds of gas and dust are giving rise to new stars. So the Eagle is not just a visually dramatic object. It is a working stellar nursery. The Eagle Nebula lies about 7,000 light-years away from Earth. That means the light we see left the nebula long before recorded human history in most parts of the world. Looking at it is therefore also looking into the past. Distance in astronomy is never just distance. It is also a built-in time machine. The broader Eagle Nebula spans roughly 70 by 55 light-years, which makes it far larger than the pillars of creation alone. This is important because the most famous picture of a nebula often shows only a tiny and dramatic piece of a much larger whole. The Eagle is an extended environment, not just a single narrow structure. What has become iconic is only one detail inside a much broader system of glowing gas and dust. The pillars of creation are only a small part of the Eagle Nebula, even though they often dominate public attention. They became famous because their shape is so striking and easy to remember. But from a scientific point of view, they are one local feature inside a much larger star-forming cloud. This helps remind us that nebulae are often far grander than their most photographed regions. The Eagle Nebula can be spotted with a small telescope, which gives it a special place among deep-sea eye objects. It is distant and enormous, yet still accessible to amateur observers. That connection between professional astronomy and backyard stargazing is one reason nebulae feel so personal to many people. Even a modest instrument can open a path toward one of the galaxy's stellar nurseries. The Eagle Nebula was discovered in 1745 by Jean-Philippe Loire de Chezeaux. This places its discovery in the era when astronomers were still building the catalogues that helped organize the sky for later generations. At that time, the physical nature of nebulae was still not fully understood. So the discovery belongs to a period when people were learning to separate simple observation from deeper physical explanation. The Horsehead Nebula is also known as Barnard 33. That catalogue name comes from the work of astronomer E. Barnard, who carefully recorded dark objects in the sky. Catalogue numbers can sound dry, but they are part of the history of careful observation. They show how astronomy moves from poetic nicknames to precise record-keeping. The Horsehead lies in Orion, near the western side of the Orion B molecular cloud. This places it inside one of the great cloud complexes associated with star formation. It is not floating by itself in empty space. It belongs to a much larger reservoir of gas and dust that helps form stars and shape the surrounding region. The Horsehead Nebula is roughly 300 light-years away. That puts it in the same broad neighborhood as some of the other famous Orion region clouds, though still very far by everyday standards. Because it is relatively nearby in galactic terms, astronomers can study its structure in fine detail. Its fame comes partly from appearance, but also from the scientific opportunity created by its distance. In visible light, the Horsehead is a dark nebula seen in silhouette against the brighter emission nebula IC 434. This is why it looks so sharply outlined in many images. We are not mostly seeing the Horsehead glowing on its own in visible light. We are seeing it because it blocks the brighter light behind it, like a shadow drawn across a luminous curtain. The Horsehead's outline resembles the head of a chess knight, which is one reason it became so famous. Human beings are very good at recognizing patterns, especially shapes that resemble familiar objects. That tendency gives many nebulae their common names. In this case, the resemblance is strong enough that the nickname has become almost as famous as the object itself. The Horsehead formed from a collapsing interstellar cloud. That means its shape is the result of gravity, density differences, radiation, and erosion, all working together over time. It was not simply carved in one moment. It emerged from a long process of cloud evolution in which some material condensed, while surrounding regions changed and dispersed. The edge of the Horsehead glows because a nearby hot star illuminates and excites the material there. This produces a bright boundary between the denser dark cloud and the surrounding luminous region. In other words, the object's dramatic outline is helped by lighting conditions as well as by structure. The nearby star acts almost like a cosmic backlight. Much of the gas around the Horsehead has already dissipated, leaving behind a denser protruding pillar. This is why the Horsehead looks like an isolated shape, even though it formed inside a larger cloud. The softer material around it has been worn away more effectively, while the denser core has endured. Its shape is therefore partly the story of what remains after erosion. Infrared images of the Horsehead reveal a glowing, gaseous landscape rather than just a black silhouette. In visible light, it seems like a dark cutout, but in infrared, the hidden structure becomes much richer. This is one of the clearest examples of how a nebula can seem to change identity when viewed in another part of the spectrum. A shadow in one wavelength becomes a textured environment in another. Some parts of the Horsehead remain opaque, even in infrared, showing that the cloud is especially dense and cold. Infrared light can pass through dust better than visible light, but not perfectly. When even infrared cannot reveal the inner regions clearly, astronomers know they are dealing with especially thick material. So those stubbornly dark patches point to some of the densest parts of the cloud. A young embedded star near the top of the Horsehead is illuminating gas from which it formed. This creates a beautiful connection between the cloud and the star. The star was born from the nebula material, and now its light is helping reveal that same material to us. It is like seeing the birthplace and the newborn together in one scene. The Carina Nebula complex contains several famous structures, including the Keyhole Nebula and the region around Eta Carinae. It is not a single simple object, but a large and varied complex with many active regions inside it. That is one reason Carina remains so important to astronomers. It offers multiple kinds of nebular physics in one connected environment. The cosmic cliffs region is part of GUM 31, which itself belongs to the larger Carina Nebula complex. This helps place the famous image in proper context. The cliffs are not an isolated formation discovered alone in empty space. They are one striking wall inside a layered and interconnected network of clouds, cavities, and star-forming material. The Carina Nebula hosts very massive stars such as WR25 and TR16244. These are not ordinary stars like the Sun. They are extremely powerful objects whose radiation and winds strongly influence the gas around them. In nebulae like Carina, the biggest stars can dominate the behavior of the whole surrounding region. Massive stars in Carina matter so much because they strongly affect the structure and evolution of surrounding gas. Their ultraviolet radiation heats and ionizes nearby material, while their winds push and rearrange it. This feedback can carve cavities, compress clouds, and expose hidden regions. So the stars are not just residents of the nebula, they are its sculptors. Eta Carinae lies about 500 light-years away in the constellation Carina. Even at that distance, it has become one of the most famous, unstable massive systems in the sky. Its importance comes not only from brightness, but from what it teaches about the lives of extreme stars. It is one of those objects astronomers return to again and again. The Tarantula Nebula's core contains the giant young cluster, R136. That cluster is the powerhouse of the region, filling it with radiation and helping make the nebula so luminous. Dense stellar clusters like this are important because they show that stars often form together in large groups rather than one by one in total isolation. R136 is an especially dramatic example of that pattern. The cluster Hodge 301 near the Tarantula is almost 10 times older than R136. This means the wider Tarantula region contains populations of different ages rather than only a single burst of formation. Star-forming complexes are often layered in time as well as in space. They preserve evidence of repeated or overlapping episodes of stellar birth. R136 contributes heavily to the Tarantula's brightness because it provides much of the energy that makes the nebula so luminous. When astronomers describe a nebula as bright, that brightness usually has a source, and in this case, the central young cluster is a major one. The stars there do not simply sit inside the cloud. They flood it with energy. A young star may have traveled about 375 light-years from R136, showing that nebular regions can launch stars far from their birthplace. This is a reminder that star clusters are not always closed, stable systems. Interactions and gravitational effects can send stars outward over time. So the wider neighborhood of a nebula can still carry traces of the cluster that formed it. The Lagoon Nebula is Messier 8, one of the most famous nebulae in the summer sky. Its Messier number places it in the classic catalogue of deep SCI objects that many observers learn early on. Yet behind that simple label is a huge, active cloud shaped by young stars and dense dust. It is both an easy catalogue entry and a complex astrophysical environment. The Lagoon Nebula is about 200 light-years from Earth. That distance makes it farther than Orion, but still near enough to study in considerable detail. Because it is both large and bright, it has become a favorite subject for both professional and amateur astronomy. It is one of the clearest examples of a bright Milky Way star-forming region. Massive embedded stars inside the lagoon emit intense ultraviolet light that ionizes the surrounding gas and makes it glow. This is a central process in many bright nebulae. Hot young stars are not just born inside the cloud. They quickly begin transforming it, turning invisible gas into visible glowing structure. the lagoon contains its own associated star cluster, NGC 6530. Clusters like this reveal that nebulae and young stars are closely linked. A glowing cloud often surrounds or contains a stellar population that formed from it. The cloud and the cluster are therefore different stages of the same larger process. NGC 6530 contains several thousand stars. That makes it a substantial young stellar population, rather than a tiny local grouping. In such crowded regions, stars influence one another's environment in complicated ways. Radiation, gravity, and motion all become part of the story at once. One Hubble view of NGC 6530 looks like a roiling wall of smoke filled with stars because of the structured dust inside the lagoon. That appearance is a useful visual clue. The dust is not spread evenly, but shaped into lanes, ridges, and folds, which give the region its dramatic texture. The result looks almost like weather, though it is unfolding on a far grander scale. Visible light images of the lagoon emphasize colorful swirls and dark pillars. These features show where glowing gas and obscuring dust lie side by side. The contrast between the two is part of what makes nebulae so visually compelling. It also helps astronomers understand where material is dense, where it is ionized, and where younger stars may still be hidden. Near-infrared images of the lagoon reveal stars hidden inside the cloud and many background stars beyond it. This again shows how much the appearance of a nebula depends on the wavelength used to study it. What looks crowded in infrared may seem veiled in visible light. The same object can therefore tell very different stories depending on how it is observed. The Trifid Nebula is Messier 20, also catalogued as NGC 6514. Its double identity reflects the fact that different catalogues were built for different purposes and eras. For many observers, the Messier number is the familiar one, while the NGC number connects it to a broader survey tradition. Both names point to the same deeply structured star-forming region. The Trifid lies about 9,000 light-years away in Sagittarius. That makes it more distant than many of the best-known nebulae often shown in beginner astronomy. Even so, it is striking enough to stand out in photographs and telescopic views. Distance does not prevent it from being one of the sky's more recognizable nebula forms. The Trifid gets its name from 3 dark dust lanes that divide the glowing nebula into 3 main parts. This is a beautiful example of dust shaping not only the structure of a nebula, but also its name and public identity. Without those dark lanes, the Trifid would not look the same and might not be remembered the same way. The shadows help define the whole object. The Trifid is a well-known region of star formation inside the Milky Way. That means the glowing cloud is not merely decorative gas, but an environment where new stars are actively emerging. Star-forming nebulae are especially valuable because they allow astronomers to examine multiple stages of stellar birth at once. The Trifid is one of those places where the process becomes visible. A dense cloud in the Trifid shows 2 finger-like jets protruding from it. Such jets are signs of energetic activity connected with very young stars. They reveal that even inside a larger nebula, small local events can produce narrow, directed structures. In other words, a nebula is not only shaped on large scales, it is full of smaller dramas too. Each of those Trifid jets is about 3/4 of a light-year long. That may sound small compared with an entire nebula, but it is still an enormous structure on human terms. A jet of that length shows how powerful even a young forming star can be. Small central sources can create surprisingly extended features. Radiation from a nearby massive star is eroding those jets in the Trifid. So even as the jets stand out clearly, they are also under pressure from the surrounding environment. This tells us that stellar birth does not happen in peace and isolation. Young structures often grow inside regions already dominated by stronger neighboring stars. The tips of the jets in the trifid may be forming new stars. If so, that would mean that jets are not only byproducts of star formation, but possible sites of further formation at their ends. It is a good example of how one process in a nebula can feed into another. A feature created by young stars may help shape the conditions for more stars to appear. In a column-color mapping of trifid images, hydrogen and sulfur appear red, while oxygen appears green. This kind of color assignment helps separate different gases visually, so astronomers can trace the structure more clearly. To a viewer, the image may simply look vivid and dramatic, but beneath that beauty is a coded picture of chemical distribution. The Rosette Nebula is a giant star-forming region in Monoceros. Its name comes from its broad, flower-like appearance, but physically it is a vast cloud of gas and dust energized by young stars. Like other major nebulae, it combined beauty with active astrophysical processes. The soft shape hides a very energetic interior. The rosette is about 100 light-years across, making it a truly large nebula structure. When people look at a photograph, that scale is easy to miss. It may appear like a modest ring on a screen, but in reality it spans a distance far beyond anything in our everyday world. Size is one of the hardest cosmic facts for the mind to hold on to. The rosette lies about 5,000 to 200 light-years away. At that range, astronomers can still examine important detail while appreciating the nebula as a large whole. Its combination of distance, size, and brightness makes it a valuable object for studying how star clusters shape surrounding gas. It stands at a useful middle ground between nearby and remote nebula regions. The rosette is estimated to contain around 10,000 times the Sun's mass. That tells us it is not a thin decorative shell, but a major reservoir of matter. Clouds on this scale can support large amounts of star formation and can continue to evolve for long periods. A nebula like the rosette is a significant galactic structure, not a small local cloud. Intense radiation from young stars inside a cluster causes rosette gas to glow. This repeats a theme seen across many star-forming regions. The newborn stars begin transforming the material around them almost immediately. The cluster and nebula therefore evolve together. The stars emerge from the cloud, and then their energy starts to reshape it. As astronomers zoom more closely into the Rosette Nebula, some Hubble views show dark hydrogen clouds threaded with dust standing out in silhouette. These darker structures are important because they reveal where the material is thicker and denser than the glowing gas around it. In a wide photo, the rosette can look soft and smooth, but close-up study shows it is full of texture, contrast, and hidden structure. That is often true of nebulae in general. The closer scientists look, the more complicated the clouds become. One small region imaged by Hubble in the rosette is only about 4 light-years across, which is tiny compared with the full nebula. That gives a sense of how much detail can exist inside a much larger cloud. A person might look at the rosette as one big glowing form, but in reality, it contains many smaller regions with their own shapes, densities, and histories. This is part of what makes nebulae so rich for study. A single famous object can contain an entire landscape of smaller structures within it. Herschel infrared observations of the rosette revealed dusty cocoons containing massive embryonic stars. These are stars still forming inside thick envelopes of material, not yet fully exposed to view. Infrared light is especially useful here because it can pass through dust better than visible light can. So instead of seeing only a glowing shell, astronomers can look into the hidden parts where the next generation of stars is still taking shape. It turns the nebula from a picture into a process. Some of those rosette embryos are expected to grow to around 10 times the Sun's mass. That matters because stars of that size do not live quietly. Once they fully form, they will pour out strong radiation and powerful winds that can reshape their surroundings. So when astronomers detect these embryos, they are not only finding hidden stars, they are catching the early stages of future major influences inside the nebula. Smaller points seen near the center of that infrared rosette image are lower-mass stellar embryos. This shows that not all stars forming in the nebula are giant ones. Star-forming regions usually create a range of stellar sizes, from relatively modest stars to much more massive ones. That mixture is important because it reflects how nebulae do not produce identical objects. Instead, they create diverse stellar populations that will evolve in different ways over time. The Witch-Head Nebula is a reflection nebula associated with the Orion region of the sky. Unlike an emission nebula, it does not mainly glow because its gas is being ionized. Instead, it shines by reflecting the light of nearby stars from its dusty material. That makes it a useful contrast to brighter red star-forming nebulae. It reminds us that not all nebular beauty comes from the same physical cause. Its nickname comes from a profile that resembles a witch's face. This is another example of how human pattern recognition influences the common names given to deep-sea objects. People often remember a nebula more easily when it resembles something familiar. The scientific structure is real, but the name reflects the way human imagination responds to shape and shadow. Wise infrared data show the Witch-Head glowing because dust is being struck by starlight. This is important because it reveals the dust directly, rather than only showing its effect in visible light. Infrared observations often make dusty regions seem more alive and active than they do in ordinary photographs. What looks faint or ghostly in one wavelength can appear full and luminous in another. Astronomers report that baby stars are brewing inside the Witch-Head's billowy clouds. That makes the object more than just a scenic reflection nebula. It is also a place where stellar birth may be underway. This is a good reminder that one nebula can play more than one role at once. A dusty cloud can reflect light, hide young stars, and help create new ones at the same time. The Witch-Head is estimated to be hundreds of light years away. That puts it relatively nearby on the scale of the galaxy, even if it is unimaginably far in everyday terms. Because of that distance, astronomers can study it as part of the broader Orion neighborhood. Nearby nebulae are often especially valuable because their structures can be seen with better detail than more distant ones. The Veil Nebula is the visible part of the much larger Cygnus Loop supernova remnant. What people usually admire in photographs is only one section of a broader, expanding structure. That is common in astronomy, where the most recognizable view is often just a slice of something much larger. The veil is therefore both a beautiful object in its own right and one visible edge of a much wider remnant. The Veil Nebula lies about 100 light-years away in the constellation Cygnus. This distance is close enough for astronomers to study the remnant structure in impressive detail. At the same time, it is far enough away that the full object stretches across a wide area of the sky. Distance affects not only brightness, but also how much of an object we can appreciate as a coherent whole. The veil spans about 110 light-years, which is enormous for something that appears so delicate in images. This contrast between fragility and scale is one of the striking things about nebulae. The veil can look like lace or torn fabric, but it is actually spread across a region vastly larger than our solar system. Fine appearance does not mean small size. On the sky, the full veil covers an area about 6 full moons wide. That means if human eyes were sensitive enough to see all of it clearly at once, it would look huge overhead. Many people do not realize how large some nebulae are in angular size because they are too faint to notice easily. The Veil is a good example of something that is both broad and subtle. The Veil's source star was about 20 times the mass of the Sun, a star that massive lives quickly and ends violently compared with a Sun-like star. Its life would have been dominated by strong radiation, high temperatures, and a relatively short existence. The remnant we see now is the aftermath of that extreme stellar life. That massive star exploded roughly 10,000 years ago, producing the Cygnus Loop remnant seen today. In cosmic terms, this is fairly recent. It means the Veil is a relatively young remnant, still carrying the visible marks of an expanding explosion. We are looking at debris that has not yet fully mixed back into the surrounding interstellar medium. A smaller Hubble description gives the age as about 8,000 years, showing that age estimates for remnants can vary a bit depending on method and rounding. This is normal in astronomy. Different models, datasets, and definitions can lead to slightly different values without changing the broad picture. What matters most is that the remnant is young enough to remain dramatically structured. The Veil gets its name from its delicate, draped, filamentary appearance. The word fits because the remnant seems to hang across space like thin cloth or mist. Yet those filaments are not decorative accidents. They are the visible signatures of shock waves, heating, and compressed gas left behind by a supernova. Those filaments are made of ionized gas shaped by supernova shock waves. A shock wave sweeps through surrounding material, compressing it, heating it, and making it glow. That is why the filaments often look so sharp and thread-like. They are the outlines of regions where violent energy has been deposited into interstellar gas. Hubble close-ups of the Veil show only tiny fractions of the full remnant. This is an important point because high detail often comes with a narrow field of view. When astronomers study small sections of the Veil, they can analyze the filaments closely, but they also have to remember that those pieces belong to a much larger, expanding structure. Nebulae often require both close-up and wide-angle thinking. The Ring Nebula is Messier 57, one of the most famous planetary nebulae in the sky. It is often shown in astronomy books because its shape is so clean and memorable. But beyond its beauty, it is also a classic example of what happens when a sun-like star reaches a late stage of life. It gives astronomers a relatively clear case study of stellar shedding and illumination. The Ring Nebula is the glowing remains of a sun-like star. That means its parent was not one of the giant stars that explode as supernova. Instead, it was a more moderate star that eventually cast off its outer layers. The glowing gas now seen around it is material that once belonged to the star itself. It lies roughly 2,000 to 2,500 light-years away. That range appears because distance measurements in astronomy can involve uncertainty and improvement over time. Even with that uncertainty, the ring is still near enough to be a favorite target for observation. It has become one of the best-known planetary nebulae partly because its size, brightness, and distance make it practical to study. The Ring Nebula is often described as an archetypal planetary nebula. In other words, it is one of the standard examples people use to explain what planetary nebulae are. It has the kind of shape and central structure that makes the class easy to visualize. When people imagine a planetary nebula, this is often the image that comes to mind. It formed when a star threw off its outer layers as it ran out of fuel. This was not a sudden supernova-like explosion, but a later-life shedding of material. The hot remnant at the center now illuminates those expelled layers. So the nebula is both a farewell display and a physical record of the star's final transition. Webb observed the ring nebula in remarkable detail, especially in infrared light. Infrared data are especially useful because they reveal cooler dust and subtle structure that visible light alone can miss. So even a very well-known object can become newly surprising when studied with better instruments. Familiar nebulae often still have hidden layers waiting to be seen. The ring's apparent magnitude is about 8.8, which means it is a good telescopic target rather than a naked eye one. This helps explain why it became popular in observational astronomy, but not a bright object noticed casually by everyone. Many classic deep-sea eye objects live in this middle ground. They are not obvious to the eye, but they reward even modest telescopes beautifully. The Ring Nebula lies in the constellation Lyra. That location has made it a common target for skywatchers in the Northern Hemisphere, especially in seasons when Lyra is prominent. Constellations serve as maps for finding nebulae, galaxies, and clusters. So knowing where Lyra is helps turn an abstract object name into something reachable in the sky. The Southern Ring Nebula is also known as NGC 3132. Like many well-known nebulae, it carries both a common name and a catalogue number. The common name helps the public remember it, while the catalogue number places it precisely within astronomical records. Both are useful, depending on whether the goal is storytelling or exact identification. The Southern Ring is a planetary nebula, nearly half a light-year in diameter. That may sound modest compared with giant star-forming regions, but it is still an enormous shell of expelled stellar material. It shows that even stars more like the Sun can leave behind structures of impressive size. A dying star does not vanish quietly. It can reshape a significant volume of space around it. It lies about 2,000 light-years from Earth. That makes it distant, but still close enough for high-resolution space telescopes to examine its structure carefully. Objects at this scale and distance are excellent for understanding how planetary nebulae are shaped. They are far enough away to see as complete systems, yet close enough to study in detail. Webb's infrared data brought a second, dying or companion star in the Southern Ring into clear view. This matters because multiple stars can strongly affect the shape of the gas around them. A nebula that looks simple at first may actually be the product of gravitational and dynamical interaction between more than one star. Infrared observations can uncover those hidden partners. Detailed study of Webb observations suggests several stars may have helped shape the Southern Ring's gas and dust. One interpretation even suggests the system may involve as many as 5 stars. If that is correct, it means the nebula's appearance is not simply the result of one star losing mass in isolation. Instead, it may be the product of a small stellar family influencing the outflow together. The Southern Ring was chosen as one of Webb's first public image targets because it shows stellar death in such vivid detail. It demonstrates how a star can cast off shells of matter and how those shells can be sculpted into rich structure. Choosing it as an early showcase also sent a message. Even familiar kinds of nebulae still hold new discoveries when seen with a more powerful telescope. Planetary nebulae like the Southern Ring contain expelled gas and dust that can later contribute material to future stars and planets. In that sense, they are part of the recycling system of the galaxy. Matter that once belonged to one aging star will eventually mix into new clouds and may later help form entirely new systems. The end of one star helps supply the beginning of others. The Helix Nebula is a nearby planetary nebula in Aquarius. Because it is relatively close, it has become one of the most important objects for studying the fine structure inside this class of nebulae. Nearby objects are often especially valuable because their details can be resolved more clearly. The helix is a good example of how proximity creates scientific opportunity. The helix lies about 700 light-years away, which is close on the scale of nebulae. That closeness allows astronomers to examine small features that would blur together in more distant planetary nebulae. So the helix is not only visually interesting, it is also one of the best laboratories for understanding what expelled stellar gas looks like up close. The helix contains many so-called cometary knots with glowing heads and trailing tails. These structures are not comets, but dense little clumps of material shaped by radiation and flow. Their appearance gives astronomers clues about how finiscale structures form during the late stages of a star's life. They show that a planetary nebula is not a perfectly smooth shell, but a richly textured environment. Those cometary knots were probably formed during the dying star's final stages. That means they preserve information about how the outflow behaved as the star was shedding material. They may mark local variations in density and the way radiation later sculpted those denser pockets. In this way, the small structures become records of the final history of the star. A portion of the helix observed by Webb highlights fierce stellar winds interacting with older gas layers. This is important because it shows that nebula shaping does not stop the moment gas is ejected. Later winds can collide with earlier material, making the structure more complicated over time. A planetary nebula can therefore be layered history, not one single event frozen in space. The helix shows how material shed by a dying star can continue interacting with its surroundings long after the initial ejection. Even after the star has cast off its outer layers, the story is still not over. Radiation, winds, and motion keep changing the cloud. So the nebula is not just debris. It is an evolving environment. Each helix cometary knot is at least twice the size of our solar system. That is astonishing, because these features look tiny compared with the full nebula. Their apparent smallness is only relative. Even the small structures inside nebulae can be vast by human standards. Each tail in those helix knots can stretch for about 100 billion miles. Distances like this are hard to imagine because there is nothing similar in daily life. The important point is that these are not tiny details in any ordinary sense. They are immense structures produced by a dying star, spread across a cloud hundreds of light-years away. Some helix filaments appear embedded along the inner rim of the nebula's gas ring. This suggests the structure is layered and organized, not simply random. Certain kinds of material gather or survive in particular zones, where geometry and radiation conditions differ. That helps astronomers understand how the whole nebula is put together. The Cat's Eye Nebula is NGC 6543, one of the most intricate planetary nebulae known. It is often discussed because its inner structure is far more complicated than a simple glowing shell. When astronomers call it complex, they mean it contains multiple overlapping patterns that require explanation. It is a reminder that stellar death can produce astonishingly elaborate results. The Cat's Eye lies about 3,000 light-years away. At that distance, it remains well placed for detailed imaging while still presenting itself as a coherent object. This balance helps astronomers analyze both its full shape and its smaller features. It is far enough to see as a whole, yet close enough to reveal layers within layers. It is considered one of the most complex planetary nebulae known. That complexity includes shells, jets, knots, and nested structures that make the object difficult to explain with a simple one-stage model. Instead, astronomers think multiple episodes of ejection and shaping may be involved. The Cat's Eye is therefore almost like a puzzle built from gas. Hubble revealed concentric gas shells, fast jets, and shock-induced knots in the Cat's Eye. Each of these features points to a different physical process. Shells can trace repeated mass loss episodes, jets can signal directed outflows, and shock-induced knots reveal where material has been compressed and heated. Together, they show that the nebula is a record of several overlapping events. The nebula shows a bullseye pattern of 11 or more concentric rings or shells. This gives the impression of repeated layers spreading outward from the center. Such patterns are valuable because they suggest the parent star did not lose mass in one smooth, continuous way. Instead, the outflow may have varied over time, producing a sequence of structures. Each bright ring in the cat's eye is actually the projected edge of a spherical bubble. This is a useful lesson in astronomy because two-dimensional images can be misleading. A ring on the sky may not be a flat circle at all. It may be the visible edge of a three-dimensional shell seen from a particular angle. The cat's eye is estimated to be about 1,000 years old. That makes it fairly young as planetary nebulae go, and helps explain why its structures remain so prominent. Younger nebulae often preserve sharper features before they disperse further into surrounding space. So the cat's eye offers a relatively fresh view of this late stellar phase. Astronomers suspect the cat's eye's bright central source may be a binary system because of its unusually intricate structure. A companion star can disturb outflowing gas, redirect matter, or help generate jets and asymmetries. This idea has become increasingly important in nebular research. Many of the strangest shapes may be clues that more than one star was involved. The Dumbbell Nebula is Messier 27, and it holds a special place in astronomy because it was the first planetary nebula ever discovered. That means it became one of the earliest examples of this strange class of glowing stellar remains. Long before astronomers understood exactly what planetary nebulae were, this object was already showing them that dying stars could leave behind visible shells in space. So the dumbbell is not only scientifically important, but historically important as well. Charles Messier recorded the Dumbbell Nebula in 1764. At the time, his cataloguing work was meant largely to help observers avoid confusing fuzzy sky objects with comets. In a way, that practical effort ended up building one of astronomy's most famous object lists. So when we mention Messier 27, we are also remembering a time when the sky was being organized, object by object, long before modern astrophysics could fully explain what those objects were. The dumbbell was formed when an old star shed its outer layers into space. This is the same broad process behind planetary nebulae in general, but each individual example shows its own shape and texture. In this case, the expelled gas created a form that looked distinctive enough to earn a memorable nickname. The object is therefore both a record of stellar aging and an example of how different late-stage outflows can take on different appearances. Messier 27 contains many knots of gas and dust. These knots show that the nebula is not smooth and uniform, even if its broad shape may appear simple from a distance. Instead, the expelled material is full of clumps and uneven structure. That tells astronomers that the final stages of a star's life can produce very textured outflows, shaped by local density differences and later radiation. The little Dumbbell Nebula is Messier 76. Its name immediately links it to Messier 27, even though it is its own distinct object. The nickname comes from a somewhat similar pinched appearance, which helps observers remember it. In astronomy, such names are useful because they connect appearance with identification, making objects easier to recall in a sky full of catalogue numbers. Messier 76 is one of only 4 planetary nebulae in the Messier catalogue. That small number makes it stand out because the Messier list contains many kinds of objects, including clusters, galaxies, and nebulae of other types. So M76 belongs to a very select subgroup within a famous catalogue. This gives it extra historical interest, not just physical interest. The little dumbbell lies about 400 light-years away in Perseus. That places it farther away than some of the most familiar planetary nebulae, but still close enough to study in useful detail. Distance affects how bright and large an object appears, but not whether it can reveal important structure. M76 remains a valuable example of how dying stars shape their expelled gas. Its nickname comes from a two-lobed shape that resembles a balloon pinched in the middle. That image helps capture the geometry in a very human way. Many nebulae receive names like this because the mind naturally tries to compare cosmic shapes with everyday forms. In this case, the comparison also hints at the physical structure. A nebula with two expanding sides separated by a narrower waist. Those two lobes are expanding away from a dying central star. This makes the nebula a direct sign of outward motion, not just a static cloud hanging in space. The gas did not appear there all at once, and then freeze. It was expelled and continues moving outward, carrying the history of the star's late life with it. Older Hubble images of M76 showed only one half clearly, which made the double-lobed nature less obvious. This is a useful reminder that our understanding of an object can change as better images and broader views become available. A nebula's true shape may remain partly hidden if the framing or depth of an image is limited. In astronomy, clearer instruments often reveal not just more detail, but a different overall interpretation. A general ESA summary states that only about 500 planetary nebulae are known in our galaxy. That number is surprisingly small when compared with the vast number of stars in the Milky Way. It shows that planetary nebulae are both temporary and somewhat hard to detect. Even though many stars may pass through this phase, the visible nebula does not last long on cosmic timescales. The same ESA material notes that planetary nebulae are rare compared with the enormous overall stellar population of the Milky Way. That rarity is one reason they attract such attention. They are beautiful, but they are also brief and uncommon stages in stellar life. So every well-studied planetary nebula becomes an important example for understanding a phase that does not remain visible for very long. White dwarfs at the centers of planetary nebulae are hot, compact leftovers of stars that have lost much of their mass. They are the exposed cores remaining after the outer layers have been expelled. Even though they are tiny compared with the broad glowing shell around them, they are powerful enough in ultraviolet light to illuminate that shell. A very small central object can therefore control the appearance of a much larger nebula. Gas close to the central star of a planetary nebula can sometimes form a dense disk. This is important because it shows that the outflow from a dying star does not always spread out evenly in all directions. In some systems, material can gather in a more organized structure near the center. That central arrangement can strongly affect how the larger nebula eventually looks. In one Herschel result, a dense central disk in a planetary nebula helped create a natural microwave laser, also called a maser-like signal. This sounds almost science fictional, but it comes from very real physics. Under the right conditions, molecules in space can amplify microwave radiation in a way that resembles a laser process. These signals help astronomers probe the conditions inside otherwise hard-to-study regions. That same study argued that a binary companion is the most likely reason expelled gas was deflected into orbit around the white dwarf. In other words, the strange geometry probably did not come from one star acting alone. A second star can change the path of flowing material and create structures that would be difficult to explain otherwise. This is one of the reasons binary systems are so important in nebula research. Binary interaction is increasingly seen as a major reason why many planetary nebulae are not simple spheres. If a dying star had no companion and lost material in a very even way, the result might often be more symmetrical. But a nearby star can tug, redirect, and disturb the gas. So many of the beautiful shapes people admire may be signs of hidden stellar partnerships. R Aquarii is a symbiotic binary system surrounded by a large, active nebula. The word symbiotic here refers to two very different stars affecting one another closely. Systems like this are especially interesting because they do not remain quiet or simple. Their surrounding nebulae can become dynamic and changeable as one star feeds from or disturbs the other. R Aquarii lies only about 1,000 light-years away in Aquarius. That relative closeness makes it especially valuable to astronomers who want to study the details of binary-driven nebular behavior. Nearby systems are often the best places to test theories, because fine structure can be seen more clearly. So, R Aquarii serves as an accessible example of a complicated stellar relationship. In R Aquarii, the central pair consists of a white dwarf and a red giant. These two stars are very different stages of stellar evolution brought together in one system. The red giant is large and extended, while the white dwarf is compact and dense. Their contrast is part of what makes the system so unstable and interesting. Nebulae around binary systems can be highly changeable because one star can feed or disturb the other. This adds motion, asymmetry, and fresh energy to the surrounding gas. Instead of a simple shell drifting outward, the nebula may be continually reshaped by ongoing interaction. Binary systems therefore make nebula evolution more complicated and often more dramatic. NGC 346 is a star-forming region inside the small Magellanic Cloud. That already makes it interesting because it lies outside the Milky Way yet close enough to study well. It gives astronomers a way to examine stellar nurseries in a different galactic environment. So NGC 346 is not only a nebula, but also a bridge between local and extragalactic astronomy. NGC 346 is about 200 light-years across. That makes it a very large star-forming region, broad enough to contain many different substructures and populations of stars. In a region this size, star formation is not just a small, localized event. It becomes an entire environment with internal variation and feedback. The small Magellanic Cloud itself is about 210,000 light-years away from Earth. That distance means we are seeing NGC 346 as part of another nearby galaxy, not as a Milky Way cloud. Studying nebulae there allows astronomers to compare how star formation works under somewhat different galactic conditions. Nearby dwarf galaxies, therefore, act like useful laboratories beyond our own. NGC 346 is the largest and most massive H2 region in the small Magellanic Cloud. H2 regions are clouds of ionized hydrogen energized by hot stars, and this one is the dominant example in that galaxy. Its scale and prominence make it especially important for understanding extragalactic star formation. It is a local giant in its own galactic setting. Astronomers use NGC 346 as an archetype of massive star formation in low metallicity dwarf galaxies. Low metallicity means the gas contains fewer heavy elements than gas in environments like much of the Milky Way. This matters because the chemistry of a cloud affects cooling, dust content, and star formation behavior. So, NGC 346 helps scientists study how stellar nurseries work under conditions different from our own galaxy's typical ones. NGC 346 contains more than half of the known O stars in the small Magellanic Cloud. O stars are among the hottest, brightest, and most influential stars in the universe. Because they emit enormous amounts of ultraviolet light, they have an outsized effect on surrounding gas. A region packed with O stars is therefore a region where feedback is especially powerful. NGC 602 is another extremely young cluster in the small Magellanic Cloud associated with active nebula star formation. The word extremely young is important because it means the stars there are close to their birth stage in cosmic terms. Such regions let astronomers see star formation almost in progress. They offer snapshots of stellar youth before time smooths away the evidence. NGC 3603 is a giant galactic nebula where several stages of stellar evolution can be seen in one field. That makes it especially valuable because astronomers do not have to study each stage in total isolation. In one region, they can observe young clusters, massive stars, surrounding gas, and the effects those stars have on the environment. It becomes a kind of compressed lesson in stellar life cycles. In NGC 3603, the blue supergiant Schur 25 is surrounded by a ring and bipolar outflows of chemically enriched material. That means the star is not only bright, but has also expelled material in a structured way. The ring and outflows show that massive stars can shape their own surroundings before they ever explode. Even before death, they can leave striking marks in the nebular landscape. Massive star clusters can blow enormous cavities in surrounding gas and dust through ultraviolet radiation and violent stellar winds. When many powerful stars act together, their combined energy becomes capable of clearing out huge regions. This is one of the main ways star clusters reshape the clouds that created them. The cluster is born from the nebula, then begins hollowing it out. The Rosette, Eagle, Carina, and Tarantula nebulae all show that bright young clusters can shape entire nebula landscapes. This repeated pattern across different regions tells astronomers that the effect is not rare or accidental. Hot stars consistently act as major sculptors of their environment. So the architecture of many nebulae is really the visible result of stellar feedback. Nebulae are among astronomy's strongest laboratories because they let scientists watch feedback from stars happening on grand scales. Feedback here means stars changing the very clouds from which they formed. Instead of only studying stars as isolated objects, nebulae allow astronomers to study relationships: star to cloud, radiation to gas, wind to dust, and explosion to remnant. They are places where causes and effects can often be seen directly. A new Gaia-based three-dimensional map traced star-forming regions in the Milky Way using 44 million ordinary stars and 87 O-type stars. That kind of project shows how modern astronomy combines enormous data sets to understand the structure of our galactic neighborhood. Instead of looking only at single objects, scientists now build spatial maps of many regions together. This helps reveal how stellar nurseries are arranged in the galaxy as a whole. That Gaia map extends out to about 4,000 light-years from the Sun. Within that volume, astronomers can study where major star-forming regions lie relative to one another in 3 dimensions. This matters because the galaxy is not flat from our point of view, and sky position alone can be misleading. A map that includes depth gives a more realistic picture of where nebulae truly are. O-type stars are crucial in mapping stellar nurseries because their brightness and intense ultraviolet output mark recent star formation. These stars do not live very long, so when astronomers see them, they know a region must be relatively young. In that way, O-stars act almost like signposts. They point to places where star formation happened recently enough that the most massive newborn stars are still around. The three-dimensional structure of nebulae matters because flat images can hide whether gas is arranged as rings, bubbles, lobes, or cavities. What looks like one shape in a photograph may turn out to be something quite different in space. This is one of the big challenges in astronomy, turning a two-dimensional view into a three-dimensional understanding. Nebulae often teach that appearances can be deceptive. The homunculus nebula around Eta Carinae has been modeled in 3 dimensions to understand how its lobes were shaped. This kind of work helps astronomers go beyond simple photographs and test physical ideas about outflow and geometry. A nebula that looks symmetrical from one angle may prove more complicated when reconstructed in space. Three-dimensional modeling helps convert beauty into mechanism. The cosmic cliffs have also been explored in 3D to show their place inside a much larger cavity and dust complex. This is helpful because the original image looks like a standalone landscape. In reality, those cliffs are part of a far wider carved region. 3D study restores the context that a dramatic close-up can sometimes hide. Some nebulae that look smooth from Earth are actually tangled systems of sheets, bubbles, and filaments. This is a powerful reminder that distance softens complexity. A cloud that seems uniform from far away may be full of internal walls and strands when studied closely. Nebula simplicity is often only an illusion created by scale and perspective. Nebula filaments in supernova remnants are often created where shock fronts compress and heat gas. That means the thin glowing strands are not random decorations, but physical signatures of a blast wave interacting with matter. Shock compression raises density and temperature, making the gas stand out visibly. Filaments are therefore traces of energy moving through space. Nebula rings in planetary nebulae can record repeated episodes of mass loss from the parent star. Instead of one smooth shedding event, the star may lose material in pulses or stages. Those stages can leave layered structures behind. So, a ringed nebula can function almost like a historical record of how the star's final outflow changed over time. Dust is central to nebula physics because it both blocks visible light and re-radiates energy in the infrared. This gives dust a double role. It hides some parts of a nebula from ordinary view, but it also makes those parts visible in another wavelength range. Dust is therefore not just an obstacle to seeing. It is also a source of information. Infrared observatories are especially powerful for nebulae because they can reveal embedded stars still hidden in their birth clouds. Visible light often gets stopped by thick dust, but infrared can pass through more easily. This means infrared images often turn dark clouds into busy nurseries full of hidden points of light. In many cases, infrared astronomy reveals the real activity behind the visible curtain. Visible light nebula images emphasize ionized gas, while infrared images often emphasize dust, cooler material, and hidden stars. Neither view is more true in an absolute sense. Each highlights different physical ingredients. Astronomers need both in order to understand what is actually happening inside the cloud. Some nebulae, like the Horsehead, change identity depending on wavelength, dark in visible light, structured and glowing in infrared. This is one of the clearest demonstrations that astronomical objects are not defined by one appearance alone. The same cloud can look empty, opaque, active, or luminous, depending on how it is observed. Wavelength changes perspective as much as location does. Nebula clouds can be both destructive and creative at once, because radiation that erodes clouds can also compress surviving clumps and influence future star birth. This is one of the most elegant ideas in nebula science. The same force that tears matter away may also help concentrate matter elsewhere. So, star formation and cloud erosion are not separate stories, but deeply linked ones. In the Trifid and Eagle nebulae, radiation from massive stars is actively reshaping small, dense clouds. These regions show that feedback does not operate only on giant scales. It also works on the level of individual pillars, knots, and compact structures. By studying those local changes, astronomers can better understand how large nebula patterns emerge from many smaller interactions. In Orion, ultraviolet radiation from neighboring stars can interfere directly with planet-forming disks. This is especially important because it connects nebula physics to the future of planetary systems. A young star may have the raw material for planets, but if nearby hot stars strip that material away, the outcome may change. Nebulae are therefore places where astronomy's different stories meet: star birth, planet formation, and environmental danger. Nebulae help astronomers study not only star birth, but also how hostile nearby environments can be for young planetary systems. A stellar nursery is not always gentle. It can be crowded, brightly irradiated, and full of disruptive forces. So when scientists study nebulae, they are also asking a deeper question. Under what conditions can young systems survive long enough to make planets? The brightest and hottest young stars are disproportionately important in nebulae because they dominate the ultraviolet budget, even though they are much rarer than cooler stars. This means a few massive stars can influence a whole region far more than their small numbers might suggest. Their light and winds shape the cloud, define its glow, and affect nearby disks and clumps. In nebulae, power is not evenly distributed. The Tarantula Nebula is especially valuable to astronomers because it is close enough to study in impressive detail, yet extreme enough to resemble giant starburst regions in other galaxies. In other words, it gives scientists a nearby example of conditions that are often seen only much farther away. That makes it a kind of bridge between local astronomy and the study of more distant, more violent stellar nurseries. By understanding the tarantula well, astronomers gain clues about far larger systems they cannot examine as closely. The tarantula's central cluster may eventually resemble a globular cluster in its overall structure. That is an interesting idea because globular clusters are usually thought of as ancient, tightly packed systems full of old stars. Here, astronomers are looking at a very different stage, when a dense stellar grouping is still young and energetic. Studying such a region may help explain how some of the universe's most crowded star systems come to look the way they do over time. The Trifid Nebula is a classic example of a mixed appearance nebula because it combines glowing gas with bold, dark dust lanes in a single object. This makes it visually striking, but it is also scientifically useful. It shows that one nebula can contain several different physical conditions at once, rather than belonging neatly to only one simple category. In practice, nature often mixes emission, dust absorption, and reflection into the same broad cloud. The Orion and Eagle nebulae show that even famous bright nebulae are threaded with dark, dusty structures that hide younger stars. A glowing cloud may look open and visible from a distance, but inside it there are often denser regions where ordinary visible light cannot easily pass. These darker lanes are not empty gaps. They are important reservoirs of material, and often the places where the most deeply hidden stages of star formation are taking place. The rosette and horsehead show that dust can define a nebula's character just as much as glowing gas does. In some cases, it is the dark structure that gives the object its famous appearance. Dust is not just background clutter around the brighter parts. It determines what gets hidden, what gets outlined, and how the whole nebula is perceived by both scientists and the public. The energy source of the Crab Nebula today is not simply leftover heat from the original supernova. It is strongly powered by the active pulsar wind at its center. That means the remnant is still being energized from within, long after the initial explosion itself. Instead of only fading passively, the crab remains dynamic because its central neutron star is still injecting motion and energy into the surrounding cloud. By contrast, A planetary nebula is mainly lit by ultraviolet radiation from a hot white dwarf, heating the gas that star previously expelled. This is a much gentler process than the aftermath of a supernova. The white dwarf is not blasting the nebula apart in the same way a pulsar wind can energize a remnant like the crab. It is illuminating the shed layers, making them glow as the system gradually disperses. Planetary nebulae are often highly symmetrical at first glance, but close-up imaging usually reveals knots, jets, multiple shells, and irregular flows. This is one of the reasons they remain so interesting, even after many have been known for a long time. From far away, a nebula may look like a neat ring or oval. Up close, it often turns into a much more complicated record of motion, timing, and interaction. The Cat's Eye and Southern Ring nebulae both suggest that companion stars can strongly complicate a dying star's final outflows. A nebula may look like the work of one star shedding gas, but in some cases, the geometry points to hidden help. Binary or multiple star systems can bend, concentrate, or redirect the escaping material. That means some of the most elegant patterns in these nebulae may actually be signatures of stellar relationships, rather than solitary stellar death. The Helix Nebula shows that even a relatively nearby planetary nebula is full of fine clumps rather than smooth, evenly spread gas. This is important because it changes the way astronomers think about such objects. Instead of a tidy bubble expanding into space, the helix reveals a far more textured and uneven environment. The details matter because they tell us about how matter was lost and then shaped afterward. The Veil Nebula shows that a supernova remnant can look fragile and lace-like even though it was created by a violent explosion. This contrast is one of the most beautiful lessons nebulae offer. A catastrophic event can leave behind something delicate in appearance, with fine threads and filaments that seem almost soft. But every strand in that apparent softness was produced by intense energy moving through gas. The Crab Nebula shows that a nebula can remain active for centuries after a supernova if a pulsar keeps injecting energy into it. So not all nebulae fade in the same way or on the same schedule. Some continue being reshaped from the inside long after the original outburst is over. That makes the Crab an especially vivid example of a remnant that is still alive with motion. Nebulae can span an enormous range in size, from small cometary knots in the helix to giant star-forming complexes like Carina and the Tarantula. This shows that nebula is a broad term, not one that refers to a single standard scale. Some nebula features are localized and compact, while others stretch across regions almost impossible to imagine. The same label covers both tiny internal detail and galaxy-scale significance. Some nebulae are small enough to fit within a fraction of a light year, while others extend across tens or even 100 light years. That difference is important because it reflects the wide range of processes involved. A local outflow around one dying star is very different from a giant cloud complex shaped by many hot young stars. Yet both are part of the same general family of luminous or dusty interstellar structures. Nebulae are chemically revealing because different filters can highlight oxygen, hydrogen, sulfur, and dust-rich regions in different ways. This means an image can act almost like a map of ingredients rather than just a pretty picture. By separating light from different elements, astronomers can tell where certain kinds of gas are concentrated. So the colors and contrasts in nebula images often carry direct physical meaning. High-energy radiation can make nebula edges look especially bright because gas glows where the radiation front strikes it and ionizes it. These bright edges are often places where one physical condition turns into another. They mark boundaries between more strongly energized outer layers and less affected interior material. In this way, a nebula rim can behave like a visible outline of an invisible process. Dense clumps often cast shadows or survive longer than the surrounding material, creating pillars, knots, and globules within brighter nebula regions. These structures are important because they reveal how uneven the original cloud was. The nebula is not a uniform fog. It is a place where density differences matter, and where those differences help decide what gets erased and what remains standing. In star-forming nebulae, erosion and compression can happen side by side within the same cloud. One part of the cloud may be losing material under harsh radiation, while another part is being squeezed into greater density. This is one reason nebular evolution is so complex. A single environment can contain both the destruction of old structure and the preparation for new star birth. Nebulae often reveal timescales that feel enormous to people but short to stars. A cloud structure might survive for millions of years and still count as temporary by cosmic standards. This can be hard to grasp because human experience is far too short to feel that kind of change directly. Astronomy helps by showing how even very slow transformations can still be part of an ongoing, evolving system. The Horsehead Nebula may last only a few million more years, which is brief compared with the lifetimes of many stars. That tells us that even one of the sky's most iconic shapes is temporary. Its silhouette feels timeless in images, but it is actually a passing stage in a larger story of cloud erosion and dispersal. The universe often looks permanent when it is really just slow. The Homunculus Nebula is unusually young by nebula standards because it formed in the 19th century. That means its origin happened in relatively recent historical time rather than deep, unreachable prehistory. It gives astronomers a rare chance to connect a visible nebula directly to a known event in recorded observation. Very few nebulae feel so close to human timescales. The Crab Nebula is younger than 1,000 years in historical terms, which makes it rare among famous remnants because its explosion was actually recorded. This gives astronomers something extremely useful, a known event date tied to an existing expanding nebula. Instead of estimating the age only from physical clues, they can compare the object to historical testimony. That combination of science and written record is unusually powerful. The Cat's Eye Nebula is estimated to be about 1,000 years old, yet it already shows many nested and intricate structures. This tells astronomers that complexity can develop relatively quickly once material begins flowing outward and interacting. A nebula does not have to be ancient to become elaborate. The internal story of shells, jets, and bubbles can unfold on surprisingly short astronomical timescales. A planetary nebula can persist for tens of thousands of years before it finally disperses into interstellar space. That makes it temporary, but not fleeting in the way a human might use that word. It remains long enough to be observed and studied, yet short enough that it represents only a brief phase in the total life of the star that produced it. These glowing shells are therefore both durable and passing. Many star-forming nebulae are associated with clusters, showing that stars often form in groups rather than in complete isolation. This is an important big-picture lesson from nebular astronomy. The romantic image of one lone star quietly forming in a private cloud is often not the norm. In many cases, stars are born in shared environments where neighbors strongly influence one another. NGC 6530 is tied to the Lagoon, NGC 6600 Elevon to the Eagle, R136 to the Tarantula, and the Trapezium to Orion. These pairings show how often a nebula and a young cluster belong together as parts of the same physical story. The glowing gas is one side of the process, and the newborn stars are the other. When astronomers connect the cluster to the cloud, they are really connecting outcome to origin. The brightest stars in nebulae are often not the most numerous, but they dominate the surrounding environment through sheer energy output. This is a recurring theme in stellar nurseries. A handful of massive stars can shape an entire region more strongly than huge numbers of smaller ones. Their light and winds matter so much that they can determine how the nebula looks and evolves. The surfaces of dusty pillars can shine sharply because radiation heats the outer layers, while the interiors remain cooler and more sheltered. This is why some pillars have bright, glowing edges but dark cores. The visible contrast is telling us about different physical conditions at different depths. So a pillar is not just a shape. It is a layered object with an illuminated surface and a protected inside. Some nebular jets are so narrow and long that they stand out clearly even inside chaotic birth clouds. This is remarkable because nebulae are often full of glowing gas, dust, and irregular structure. A jet can cut through all of that complexity like a deliberate line. Its narrowness and directionality tell astronomers that even in messy environments, some processes remain sharply organized. Herbig-Haro objects are luminous shock features produced by jets from young stars, and such activity is found in the Orion region. These objects form when the jets from a newborn star slam into surrounding material and heat it. They are important because they allow astronomers to trace otherwise hard-to-see outflow activity. In a sense, they are signposts showing where a young star is actively interacting with its environment. A dark patch in a nebula is not always a solid, dense cloud. In at least one Orionaria case, infrared data showed that what looked like a dark region was actually a hole blown through the nebula. This is a powerful reminder that appearances in astronomy can be misleading. What seems like a blocking object may sometimes be an absence rather than an obstacle. Nebulae can therefore mislead the eye if they are viewed in only one wavelength. A visible image may suggest one structure, while infrared, radio, or X-ray data reveal something quite different. This is why modern astronomy depends so heavily on multi-wavelength observation. No single kind of light tells the whole truth about a cloud. Multi-wavelength astronomy is essential for nebulae because no one band of light shows all the gas, dust, stars, and energetic particles at once. Each wavelength highlights some ingredients and hides others. To understand the full system, astronomers need to combine those views. Nebulae are especially strong examples of why the universe must be studied in more than one color of light. Hubble, Webb, Spitzer, WISE, Chandra, Fermi, and radio observatories all reveal different sides of nebula physics. Some specialize in visible detail, others in infrared dust, and others in high-energy or radio phenomena. Together, they provide a much fuller picture than anyone could alone. The modern understanding of nebulae is really a collaboration across instruments, not just across astronomers. Visible light telescopes are especially good at tracing ionized gas and sharp structure in nebulae. They capture glowing edges, filaments, shells, and other forms where energized gas stands out clearly. These views often produce the most famous public images because they are vivid and detailed. But scientifically, they are one piece of a larger puzzle. Infrared telescopes are especially good at seeing through dust and tracing warm grains inside nebulae. They can reveal stars still hidden in their birth clouds and make dusty regions glow that would otherwise seem dark. This gives astronomers access to the interior life of a nebula. Infrared light often turns a blocked view into a revealing one. X-ray and gamma-ray telescopes become especially important for energetic remnants such as the crab. High-energy radiation can show where the most extreme particles and processes are at work. A visible image may show shape, but X-rays and gamma-rays can reveal the deep engine driving the system. In a remnant powered by a pulsar, that extra view is crucial. Some nebulae are famous not because they are the biggest or brightest, but because geometry makes them striking from Earth. The Horsehead and Ring nebulae are good examples. Their shapes are especially memorable when seen from our line of sight. Another viewing angle might make them appear less iconic, which means fame in astronomy sometimes depend partly on perspective. Other nebulae are famous because they are nearby laboratories, like Orion and the Helix. Their relative closeness lets astronomers study fine structure with unusual clarity. Nearby objects often become cornerstones of understanding because they can be tested in more detail than distant ones. Proximity, in astronomy, is often a scientific advantage as much as an observational convenience. Still, other nebulae are famous because they are extreme, like the Tarantula Nebula and Eta Caringe's homunculus. They push toward the outer limits of what nebula environments can do. Studying them helps astronomers understand not only ordinary cases, but exceptional ones. Extreme objects are useful because they reveal how physics behaves under the most powerful conditions. In some nebulae, chemistry is rich enough that astronomers can track hydrocarbons and other dust-related compounds through infrared emission. This means the cloud is not just simple hydrogen gas floating in emptiness. It contains a more complicated chemical environment. Infrared observations allow scientists to identify and map some of those ingredients, giving a clearer picture of the material available inside the nebula. Nebulae can be important for understanding galaxy evolution because massive star-forming regions influence how gas is heated, compressed, and dispersed on larger scales. A nebula is not only a local object. It can also affect the broader life of its host galaxy by changing the condition of interstellar material. Many such regions together help determine how galaxies continue forming stars over time. Regions like NGC 346 are especially useful because they show how star formation works in environments poorer in heavy elements than much of the Milky Way. This is valuable because not all galaxies have the same chemical history. By comparing these environments, astronomers can test how universal or flexible the star formation process really is. Different chemistry can lead to different details in how clouds behave. Regions like the Tarantula help astronomers interpret distant starburst systems that cannot be resolved nearly as clearly. When telescopes look at very remote galaxies, they may see only blended bright regions rather than detailed individual structures. The Tarantula offers a nearby template that helps decode what those unresolved regions might actually contain. It acts almost like a local translation key for distant galactic activity. Nebulae are among the best examples of how cosmic structure can arise from a few basic ingredients, including gravity, radiation, gas pressure, magnetic effects, and motion. These are simple in principle, but when combined on large scales, they create astonishing complexity. Pillars, shells, lobes, filaments, and cavities all emerge from those interacting forces. Nebulae therefore show how rich patterns can grow out of a relatively small toolkit of physics. The visual beauty of nebulae often comes from contrast. Bright rims beside dark dust, hot stars beside cold clouds, and smooth glow beside delicate filaments. These oppositions make nebulae visually powerful even before one knows the science. But the science deepens the beauty, because the contrasts are not merely artistic. They reflect real differences in temperature, density, composition, and illumination. What makes nebulae visible at all is their great size, their interaction with energetic stars, and the sensitivity of modern telescopes. Many nebulae are far too tenuous to be compared with anything like an Earth cloud. If they were small, we would barely notice them. Their visibility depends on how much space they occupy and how effectively radiation makes their material stand out. Nebulae are therefore best understood not as static clouds, but as evolving environments shaped by birth, feedback, death, and recycling. They change over time, they respond to nearby stars, and they pass matter from one cosmic generation to another. A nebula is not just a thing. It is a stage in an ongoing process. Across all types, Nebulae connect individual stars to the larger history of their galaxies. A star is born from nebular material, may later reshape its surrounding nebula, and can eventually return matter to space through winds or explosion. In this way, nebulae link the life story of one star to the continuing life of the galaxy itself. They are where local events become part of a much bigger cosmic cycle. Nebulae are major recyclers of matter, returning processed gas and dust from old stars back into interstellar space. This is one of the quiet but profound truths about the universe. A star does not keep all of its material forever. In many cases, especially late in life, it gives some of that matter back to space, where it becomes part of the wider galactic environment again. So a nebula is not only a sign of change, it is also part of the universe's way of reusing what came before. In star-forming nebulae, that recycled material can become the raw substance for future generations of stars. What once belonged to an older star may later drift into a cloud, become part of a dense clump, and eventually help build an entirely new one. This gives nebulae a deeply connected role in cosmic history. They are places where endings and beginnings overlap so completely that it becomes hard to separate them. Some nebulae contain enough chemical richness that astronomers can track hydrocarbons and other dust-related compounds through infrared emission. This tells us that nebulae are not just simple clouds of one basic ingredient. They can include more complex materials mixed into the gas and dust. By studying those emissions, astronomers learn not only where matter is, but something about what that matter is made of and how it behaves in space. Nebulae help scientists understand galaxy evolution because massive star-forming regions influence how gas is heated, compressed, and dispersed on large scales. A single nebula may look local and contained in an image, but its effects can extend outward into the surrounding galactic environment. When many such regions act across a galaxy, they help shape the future pattern of star formation. So a nebula belongs not only to the life of a few stars, but also to the larger life of its galaxy. Despite their dramatic photographs, nebulae are extremely tenuous compared with Earth's atmosphere. The material in them is spread astonishingly thinly through space. If a person could somehow drift through most nebulae, they would not encounter anything like a dense cloud in the everyday sense. Their visibility comes from their huge size and from the way light interacts with their matter, not from being thick in the way weather clouds are thick. What makes nebulae visible at all is their enormous scale, their interaction with energetic stars, and the power of modern telescopes. Even very sparse material can become detectable if enough of it stretches across a vast region and if it is lit or heated in the right way. This is one of the lessons of astronomy. Things do not have to be dense to be real, important, or beautiful. Sometimes they only have to be large, luminous, and patiently observed. The most famous nebulae are usually not isolated objects floating by themselves in empty space. They are often parts of larger molecular clouds, shells, or stellar complexes. What we call a nebula may be just one visible chapter in a broader structure that extends much farther than the famous image suggests. This reminds us that astronomy is full of connected systems, even when the eye first notices only a single glowing form. Nebulae are therefore best understood not as static clouds, but as evolving environments shaped by birth, feedback, death, and recycling. A nebula changes with time. Stars form inside it, stars illuminate it, stars erode it, and in some cases, dead stars help create it. So the nebula is not merely background scenery for stellar events. It is one of the main stages on which those events happen. Across all their different types, nebulae connect individual stars to the larger history of their galaxies. They show how a star can emerge from interstellar matter, alter that matter, and eventually return some of it to space. Through nebulae, the life of one star becomes part of a much broader cycle. They are some of the clearest places where personal stellar stories become galactic ones. Taken together, nebulae show that space is not empty background, but an active medium where matter is continually being illuminated, rearranged, and reused. This may be one of the gentlest and deepest insights they offer. What seems empty from a distance is often busy with transformation. The universe is not only made of objects, it is also made of environments in motion. The word nebula was once applied to many fuzzy-looking objects seen through early telescopes. In those earlier centuries, observers did not yet know whether such hazy patches were clouds, star clusters, or distant galaxies. The word reflected uncertainty as much as description. It is a lovely example of how language in science often begins broadly and becomes more precise as understanding grows. Modern astronomy now separates nebulae into several categories, including emission, reflection, dark, planetary, and supernova remnant nebulae. This classification helps astronomers move from appearance to explanation. Two clouds may both look beautiful, but they may shine for very different reasons or come from very different origins. Naming the type is a first step toward understanding the process behind the view. Reflection nebulae glow by scattering the light of nearby stars, rather than by generating much visible light of their own. In this sense, they are luminous by borrowing. They reveal themselves through reflected starlight instead of strong internal excitation. This gives them a quieter role among nebulae, one based more on gentle illumination than on intense ionization. Reflection nebulae often look blue because shorter wavelengths scatter more efficiently from fine dust. This is somewhat similar in principle to why Earth's daytime sky looks blue. The dust grains in the nebula interact with light in a way that favors the scattering of shorter wavelengths, so their color is not arbitrary. It is a sign of how light and tiny particles meet. Dark nebulae are seen mainly in silhouette because dense dust blocks light from brighter material behind them. They are often known for what they hide rather than what they emit. Yet that hiding is itself a form of presence. A dark nebula announces itself by interrupting the light behind it, turning absence into a kind of visible outline. Many dark nebulae are cold, dense regions where new stars can begin forming. Their darkness does not mean lifelessness. Quite the opposite. Some of the quietest-looking parts of a cloud are places where future stars are gathering slowly into being. In nebulae, concealment and creation often go together. Dust in nebulae can hide stars in visible light while allowing infrared telescopes to reveal them. This gives nebulae a layered quality, almost like veils within veils. A visible image may show only the outer surface of the story, while infrared reaches farther inward. So different kinds of light do not merely show more or less. They reveal different depths of the same reality. Infrared observations often show that a region appearing dark in visible light actually contains warm dust and embedded stars. This changes the emotional meaning of darkness in astronomy. A black patch is not always empty or silent. It may be full of hidden warmth, structure, and early stellar life waiting to be seen in another wavelength. The Orion Nebula contains hundreds of newborn stars. This makes it one of the clearest nearby examples of a true stellar nursery. Rather than seeing only one dramatic object, astronomers are looking into a place where many young stars are sharing the same environment. Orion is therefore less like a single event and more like a community in the earliest part of life. Two protostars highlighted in Orion are known as HOPS 150 and HOPS 153. Naming individual young stars inside a nebula helps show how detailed modern observations have become. Astronomers are no longer limited to describing Orion as one general cloud. They can point to specific forming stars and examine their immediate environments, turning the broad glow into a set of individual stories. Orion contains protoplanetary disks, often called proplyds, around very young stars. These disks are important because they are the kinds of structures from which planets may eventually form. This means Orion is not only a nursery for stars. It may also hold the earliest stages of future planetary systems. The nebula contains not just suns in the making, but possibly worlds in the making too. Some Orion proplyds are being stripped by intense ultraviolet radiation from nearby hot stars. This creates a sobering contrast. The same region that produces young stars and disks can also be harsh enough to damage them. Nebulae are not always gentle cradles. They can be crowded and difficult places where survival depends strongly on local conditions. In Orion, the proplyds nearest the hottest stars can appear bright, while one farther away may appear dark. This shows how the appearance of a small object inside a nebula depends heavily on its environment. Distance from hot stars changes how much radiation reaches the disk and how strongly it glows. Even within one cloud, nearby conditions can create very different visible outcomes. The disks in Orion, imaged by Hubble, range from about 2 to 8 times the diameter of our solar system. That comparison makes their scale easier to feel. These are not tiny specks in any everyday sense. They are broad structures surrounding young stars, large enough to contain the raw material for future systems, and yet still only local details inside a much larger nebula. Protoplanetary disks are thought to be about 99% gas and only about 1% dust. Even though dust often gets much of the visual attention, gas dominates the mass. This is a useful reminder that what stands out in images is not always what matters most by quantity. In astronomy, the visible and the abundant are not always the same thing. Hubble images of Orion show more than 3,000 stars in a single detailed view. That richness makes the nebula feel almost crowded with life. It is not a lonely cloud with 1 or 2 bright points, but a region densely populated with stars at different stages. Such observations turn the sky from abstraction into something more populated and textured. Orion is often called a picture book of star formation because it contains stars of many different sizes and stages. In one region, astronomers can examine newborn stars, disks, glowing gas, and the effects of radiation on surrounding material. This layered variety is why Orion remains such a central teaching object in astronomy. It does not show just one step, but many. The Eagle Nebula's pillars of creation are columns of cool hydrogen gas and dust. Their coolness matters because it contrasts with the bright, heated edges that face the nearby stars. Inside the pillar, material can remain denser and more sheltered. On the outside, radiation carves and lights the surface. The pillar is therefore a structure made meaningful by temperature difference as well as shape. The pillars also function as incubators for new stars. This gives them their deeper importance beyond their famous outline. They are not only sculpted objects to be admired from afar. They are active sites where gravity can gather material inward and begin the process of stellar birth. Their beauty is tied directly to their physical role. Their shapes are driven by high-energy radiation and strong winds from hot young stars in NGC 6611. This means the pillars owe part of their grandeur to attack as much as to shelter. Radiation strips and erodes the surroundings, leaving denser parts standing out. The result is something that looks calm in a photograph, but is born from constant pressure. The glowing edges of the pillars are ionizing flows produced as dust and gas are heated on their surfaces. These bright borders reveal where energetic light is directly interacting with the material. Such edges are like visible front lines between protected interior zones and exposed outer layers. The pillars look sculpted because, physically, they are being sculpted. The horse head survives longer than its surroundings because its material is clumpy and comparatively resistant to erosion. This is another example of how density shapes fate inside a nebula. Less dense material has already been worn away, while the denser cloud still remains. So the horsehead's famous outline is partly the story of selective survival. One estimate suggests the horsehead may disintegrate in about 5 million years. That gives the object a gentle impermanence. Even one of the most recognizable shapes in the sky is not fixed forever. Nebulae can appear timeless to human eyes, yet they are always changing slowly, always moving toward another form. A young embedded star near the top of the horsehead is illuminating the gas from which it formed. This creates a particularly intimate picture of stellar birth. The star and its birthplace are still close together, with the child lighting the cloud that made it. There is something quietly beautiful in that relationship between new light and old shelter. Massive stars in the Carina Nebula are important because they strongly affect the structure and evolution of surrounding gas. Their influence extends far beyond their own surfaces. Through ultraviolet radiation and stellar winds, they carve cavities, brighten rims, and change the density of nearby clouds. Their presence is written into the whole shape of the nebula. The Homunculus Nebula is about a light year long. That is a vast size for material thrown off in a stellar outburst associated with one system. It reminds us how much matter and energy a massive, unstable star can move into space. Even what may seem like a small nebula compared with giant star-forming complexes can still span distances beyond ordinary imagination. The outburst that made the homunculus expelled at least 10 times the mass of the Sun in gas, and perhaps more. That amount of matter is extraordinary. It shows that some stars can undergo eruptions powerful enough to reshape their surroundings on a major scale, even before their final death. The nebula around Eta Carinae is therefore a monument not only to instability, but to enormous mass loss. Modern modeling suggests the binary nature of Eta Carinae helped shape the homunculus. This adds depth to the picture because it means the nebula's structure may not be due to one star acting alone. A companion can redirect outflow, affect symmetry, and leave marks in the final shape. So what appears as one dramatic form may actually be the result of a relationship. Eta Carinae is expected to end its life by collapsing, probably with a supernova explosion. This means the famous system is still not finished telling its story. The homunculus may be only an earlier act in a larger stellar drama. In that sense, some nebulae are not only records of the past, they are signs of futures still waiting. The Tarantula Nebula is also known as 30 Doradus. Like many famous objects, it carries both a common name and a catalogue identity. The catalogue name places it within formal astronomical work, while the common name makes it memorable and vivid. Both belong to the way humans learn the sky, through precision and through imagination. The tarantula lies in the large Magellanic Cloud rather than the main disk of the Milky Way. This matters because it places one of the best-known stellar nurseries outside our own galaxy. It lets astronomers study a spectacular nebular environment in a neighboring galactic system. In that way, the tarantula is both close and beyond home. Several stars in R136 exceed 100 times the Sun's mass. Such stars are among the most extreme normal stars known. Their brightness, heat, and radiation output are so great that they become dominant forces within the nebula. They do not merely shine inside the cloud. They help determine how the whole region behaves. Some stars associated with the tarantula have been described as roughly 200 times the Sun's mass. Whether one focuses on the exact figure or the general scale, the point remains astonishing. These are stars near the upper edge of what nature seems willing to build. Their existence helps explain why the tarantula is such a fierce and luminous environment. At the same time, smaller stars are still forming in and around R136. This is a gentle reminder that nebulae are rarely about only one size or one kind of star. Even where the biggest stars dominate the light, quieter formation of smaller stars continues. Great brilliance and quiet beginnings can exist together in the same region. A young star may have traveled about 375 light-years from R136, showing that nebula regions can send stars far from where they formed. Stellar birthplaces do not always remain tightly bound to everything they produce. Over time, interactions can send some members outward. The wider space around a nebula may therefore still carry traces of its past activity. The lagoon's visible light images emphasize colorful swirls and dark pillars, while near-infrared views reveal stars hidden inside the cloud and many beyond it. This paired view captures one of the most peaceful lessons of nebular astronomy. Every cloud has more in it than first appears. What looks like a boundary in one kind of light becomes a window in another. A dense cloud in the Trifid shows two finger-like jets, each about 3/4 of a light-year long. Radiation from a nearby massive star is eroding them, and the tips may even be forming new stars. This makes the jets feel almost like small worlds of their own within the larger nebula. They are fragile, elongated, and active all at once. In common Trifid color maps, hydrogen and sulfur appear red, while oxygen appears green. This kind of mapping helps separate the nebula's ingredients visually, letting people see structure that would otherwise be harder to distinguish. The image becomes both beautiful and informative. Color, in such pictures, is not only decoration, but explanation. The Rosette Nebula is estimated to contain around 10,000 times the Sun's mass. That enormous reservoir of matter helps explain why it is such an important star-forming region. A cloud of that scale can produce clusters, glowing gas, dense pockets, and future generations of stars. It is not merely a decorative wreath in the sky. It is a major storehouse of galactic material. The Rosette's interior includes dark clouds, dust-laced silhouettes, and cocoons of embryonic stars. Some of those embryos may grow to around 10 solar masses, while smaller ones are forming nearby. This combination of large-scale beauty and hidden quiet beginnings makes the Rosette feel especially fitting for a final reflection. Inside one broad, glowing shape, many separate futures are slowly taking form. And perhaps that is one of the softest truths nebulae offer. They hold contrasts without conflict. They can be thin yet immense, dark yet full, shaped by violence yet beautiful in stillness, born from endings yet full of beginnings. As the light drifts across these distant clouds, and as old matter becomes new once more, the universe seems less like a place of separate things, and more like a long, patient exchange. In that gentle sense, the nebulae never really stop. They only keep changing, quietly, in the dark.